I can see Faiza Mustaq in the meeting. Can
Yeah, good afternoon, sir. Give me a minute, sir. Uh, good afternoon, everyone. Uh, my title is A Study of an Efficient Edge Detection Approach with Machine Learning. These are the table of content. Uh, traffic in infrastructure and performance is an important factor for economy of the country, but traditional monitoring system have limitations. That's why day by day we are moving towards an intelligent traffic system. But even now today we are not fully dependent on intelligent traffic system. If we will see on a large scale, intelligent traffic system is on like satellite based, but we cannot use it in gullies because satellite they capture the images which have they're lengthy. So and we usually install cameras which are on like majority times on the highways or the busy streets, but in gullies and all they are not still there. So right now we are somewhere to the traditional, we are not fully into the intelligent, but day by day as technology come we are moving towards it. And images, they are an essential means for conveying the information. For the purpose of properly identifying the vehicles, whether on the highways, gullies, everywhere, uh, edge detection, it is an important factor. These algorithms are important for this work. So efficient edge detection approach ensure the efficient processing of data while minimizing the errors, maximizing the data quality, eliminates the need of manual screening, which is a bottleneck to the traditional method. And in the field of edge detection, the two prominent algorithm that we have used in our work, they are canny edge detection and sobel algorithm. These two algorithms, they have a significant contribution to the domain of image processing, but each of them have a limitation. And there are a lot of image edge detection algorithms, like canny is there, robert is there, and pervets is there, sobel is there. But canny edge detection algorithm, uh, this is most frequently used and it gives better result. That is why we have taken it. And if we talk about sobel algorithm as compared to the rest of the algorithms for edge detection, this algorithm, it gives us a result in like time execution is less. That is why we have taken these two traditional algorithms for this work. Our objective is, we will compare Sobel and Kenny edge detection algorithm. We will evaluate their strength in robustness, edge detection, image connectivity, and vehicle counting. And by this analysis, we will create an improved algorithm that will combine the benefits and increase the efficiency, and our storage requirement will be reduced. We will optimize the detection. And our approach, like as I said, it will optimize the storage and connectivity of the edges will be better, and precise vehicle counting, it will give result for this also in a positive way. So this is the way, this is a methodology. Like we first capture the picture, and we will convert it into the grayscale. Then we will apply both the traditional algorithms, canny and sobel, and after that we will compare it, like what are the results on an image, and we will identify their limitations, and we will take the positive aspects from there, and we will try to make an efficient approach out of these two traditional methods and give a we can say kind of hybrid approach which will uh, uh, which will have the positive aspects of both. And then we will apply bilateral filtering, in which what we will do is it will go through the two steps. It will go through the Gaussian smoothing, as well as we will work through the gradients also to the intensity of the pixels. And in Sobel we will apply Sobel operator in the kernel of 3 into 3. And we will work on robustness also, because our aspect like our main aim is to, if we are working on an image, if we are working on any traffic, it should work in challenging conditions also, so we will impact this factor. And after that we will go to the morphological operations, because like texture analysis, that is important. And after that we will go to the vehicle counting, and then we will compare the three algorithms. So this is the first edge detection CADI. It came into the existence in 1983, and it was presented by John Kenny. The Kenny edge detector was designed to detect precise edges with high intensity. The canny operator is effective in controlling the level of detail in edge image and suppressing the noise. This suppresses the noise because it works with the Gaussian filter, and it has two threshold values. We usually work with two threshold values, which detect the weak and the strong edges, and it extract features without disturbing the image and is noise resistant. Uh, Yeah, and one more thing, with Canny Edge, what we have, like, what the outcome came was, it gives better connectivity, but time execution is more. In Sobel algorithm, it was first put forth by Erwin Sobel in 1970. While averaging, the Sobel kernel prioritizes central pixels, and it is dependent on the central pixel also. And it only works in two dimension. It can't work on apart from that, so that is somewhere a limitation for it. And Sobel operators is a fast detection speed. Yeah, it works faster than rest of the uh, algorithms. As I said it in the starting, that was the reason we took second algorithm, Sobel. And yeah, it works in horizontal and vertical, ignoring the other directions. Now about our improved algorithm. As the Sobel algorithm, this is gradient based, and the Canny, it's Gaussian based. In our improved algorithm, what we have done, we have combined it. As I said, we have done bilateral filtering here, and through the creation of an orientation histogram based on edge data. As at the time of methodology I mentioned, like textured analysis, we have added textured analysis here, so that we can clearly get the images of the car. Because for example, we are capturing the picture from a camera, as these both of these algorithms, they are supervised, right? So they know a car, what is a car, what's a tree. uh, so by this histogram they will detect the car, and it will show the car, and rest of the things it will eliminate. By that we will reduce the space, and if the space is reduced, the time execution will be less as compared to the other algorithms. So the this algorithm markedly enhanced the determination of edge detection within the image, significantly elevating overall precision and reliability in the edge detection outcomes. So here we take a picture, we convert it into the grayscale, we do bilateral filtering, and we compute the gradients using Sobel algorithms. We like using gradient magnitude and orientation, as I have mentioned here. We do non-maximum suppression. By non-maximum suppression, what happens? Those weak edges, they are eliminated. Only the edges which are near the central pixel, they are counted there, and those who are far, they are eliminated. And we do double thresholding, as like I have mentioned, they it detects the weak and the stronger one and unwanted one. and then we do the orientation histogram, and then we give the output. So we evaluated the outcome of Kenny Edge algorithm. These are the results and Sobel algorithms, and constructed our improved algorithm approach. Kenny produced finer edges. I'll be showing it after some time. Displays edge connectedness. Vehicles were recognized. However, it occasionally added extra and unwanted edges. The Kenny algorithm has a long execution of time. And about Sobel algorithm, it provides thicker edges because it works on the gradients. So it provides thicker edges, resulting in reduced precision and had edge disconnections. It has detection issues also, and it produced inaccurate finding. Sobel algorithm took less time as compared to the Canny. Uh, our improved algorithm performed well in terms of scalability and efficiency. Our suggested approach demonstrated increased edge continuity, resulting in a finer edges representation, and performed well in terms of robustness by precisely highlighting vehicles in an image. These results have a great deal of promise of to improve traffic related application and progress the science. Improved algorithm outperformed the Sobel and Canny in terms of execution of time also. So these are the time executions. We can see Canny is taking more time than Sobel, and our algorithm is taking very less time. So yeah, this is the original image of three vehicles. Here we go with the Kenny. We can see that it has a good connectivity of like edges, but somewhere it is taking unwanted lines, which can it is a bottleneck. It's unwanted. We don't need it. We just need three cars, and vehicle count is also good. But if we will talk about Sobel, there is discontinuity. It is not giving proper, it's not giving us proper results, and vehicle count is also not right. Improved one, it is giving good connectivity of edges also, and count is also right. So as I said, like errors are less, time execution is also less as compared to others. So these are the advantages. We have a disadvantage for our algorithm also, like it's little complicated and lengthy, and is little sensitive to variations. And this is a conclusion. Our improved algorithm surpasses the limitations of traditional algorithm by removing extra edges and noise from the photos. As we saw, there was a noise in Canny, and uh, edges were not proper in Sobel also, but in improved both were there. And a data set is more precise and accurate as compared to the traditional one. And our study has significance for traffic applications, since the enhanced algorithm make it possible for drivers to quickly acquire pre-trained information about traffic conditions. And these are the references.
Sir, can you explain how the car count is detected when we implement canning? That is my first question. Then why you have chosen only time as the measure to assess the performance of the algorithm other than some other
Sir,
features?
give me a minute. Wait, sorry, sir, 1 minute.
Yes. Professor Faiza.
Yes, sir.
Yes.
Sorry, sir.
Yeah, no issue. Can you explain why you have chosen only time as the measure? That is the first question. Second, how the cars are counted when we
Uh,
implement edge detection alone? That is my second question.
Sir, I have taken time and I have taken robustness and connectivity of edges because when we saw there were three pictures.
That's why how you measured the robustness or connectivity in edges. Have you done any comparison with
Yes.
some? Yes.
Sir, first we have done orientation histogram, which reflects that which do the texture analysis.
But histogram shows only the pixel distribution. It's okay.
Yeah,
Leave it. No issue. Leave it.
it,
Leave
it,
that
it, it,
question.
it does that object recognition also because both Canny and Sobel they are supervised. That is why we have implemented orientation histogram, because of which they do recognition of object and they give the count.
I check it. Okay, thank you.
Okay, sir.
Maybe I may be wrong. Thank you very much,
Thank you.
Professor. Thank you very much.
Thank you.
Hello. Good afternoon to all of you. Can I present my paper now, sir?
Is this Dr. Nab?
Yeah, Dr. Bharat Bhushan Nayak, sir.
Your paper is paper number 61, right?
Yeah. Yes, sir.
Just a moment. Dr. Neb, would you mind going after paper ID 234, which is next?
Okay, no problem. No problem, sir.
In that case, next we have paper 234, deep learning based control for bilateral system with time delay by Anirudh Anand and Rohit Singla.
Yes, am audible?
Yes, you're audible.
Okay. So just wait, I am going to share my screen. Yeah, is my screen visible?
It is.
Yes, it is.
Okay. First of all, I'm wishing this RDCAP team for this great event. They are going, and Professor VK Tayal is doing chairing this session for A. So in this, I have paper 234, and I'm doing this work with my postgraduate students, Anirudh Anand EV, myself, Rohit Singla. And today I'm going to present this work. In this work, basically, we have the deep learning aspect of base control for a bilateral system with time delay, because we have to take the symmetrical time delay rather than to take the unsymmetrical, whether goes to master to slave or slave to master. So in this work, we are going to present first of all introduction, then what we have to propose model, then we result analysis, and after that we have conclude. So I will hardly take 5 to 6 minutes to complete this session. So in the introduction, first of all, the time delay in bilateral tally operation system is to make how we consider this time delay is a great issue in field of tally operation robotic system, because with the help of time delay, not only we taking up us some issues regarding the instability, transparency, also we have to unsynchronize system, because in our aim of bilateral system is completely synchronization between the two system, master and slave. But due to this time delay, we have occurred so many of problems. So we have to using the different type of control strategies in these adaptive control strategies, stochastic control strategies, deterministic approaches. And after that, we have come to use the why not we use the some AI tool to handle this type of consider the modeling of the time delay. So such method is used for the neural networks as we have the recurrence neural networks in which we have the one technique is the LSTM, is a long short term memory, is a special type of RNN architecture is addressed to basically the gradient problem. Gradient problem is to vanishing in the time delay in which we have to consider the particular range set on the initial level. So in the traditional way, the output each time depends on the various outputs, whether they have to the current input or the integer inputs. So as the time steps progress, have you not the propagated through the very small or to the dependency on the very long-term oscillations. So these LSTM approach is overcome this type of problem and introducing a memory cell, because memory cell is helping us to which type of information we need to retain and which type of information we need to omit, just like we consider a wide Gaussian noise. So store information over long periods of time. So the memory cell is controlled by three gates: the input gate, forget gate, and the output gate. So this is the proposed model in which we have the LTM based the master controller. Next we have the human operator as usual, which we have controlled the master one, the master robot. And these are the particular communication channel. The communication channel is from TM is representing from master to the slave communication is the TM, the time delay from master to slave, and the TS is showing the time is taken by the information or the communication channel from slave to the master. And this is the same environment when the operator is giving the force on the master. In the same way, the environment is pushing the force on the slave robot, which worked in the environment in the remote environment. So these are the methodology. So raw data, just like a link joint velocity, we consider the master one in the form of sequences, are fed into the predicted or trained offline to product signals for the next step. So the signal is predicted whether we take the any type of signal, whether at the initial life or we take the sinusoidal or any trapezoidal type of signals, which type of signal we have to make for our consideration value. So being an estimate for the next time of value, so there are the after the delay of the expectation of time, which we have to get the next possible time. So namely, we have to make this possible x t. So if we assume the assumption at the like a little error in the initial level, so what are the truth about the relationship between the estimated time delay or we have the actual time delay? So they we have considered this type of torque value, which we have also considered this. So therefore, in general case, the time delay in both direction can be known as by the master to slave and slave to master. So these are the time domain which we have to consider. And next is the dynamical equation of that entire teleoperation system can be represented in state space. Okay, whether these are the two equations and they represent the whether which type of A and A2 and A2. So basically, this is the mass moment of inertia matrix in which consider the all values, and W is representing the which type of system is slave from the environmental noise, and XM is particular of the human operator. So these system was modeled in the particular tracking analysis of the parametering the estimation error. So in spite of that, the parameter estimation error by giving the four data, just like a two link masses and two link lengths, L1, L2, and M1, M2. So rather than to given the these information, so we have to want the robot itself to take rather than to giving than modeling these information again and again. We have to make the sensitivity analysis with the help of this Keras library to model the pre-trained LSTM network. Whether we have to give the information one time, the LSTM has a forget gate to use this information. So we have the pre-trained model is in the similar way which we have the already teleoperating system. So here is the model of two particular novelty of AS2 predictor and estimator function to determine the future state of physical parameters, rather than the user to need to give the again and again of this parameter. So control signal to slave reduce the error and stabilize the signal much sooner. So the particular time delay of the system itself have to make the signal and dynamic model of the system in many ways. In this case, we have to make the random time signal, just like we have to choose the random white Gaussian noise. Uh, we have also considered the different type of noise, just a jerky noise, Levy noise. But we have considered for the general point of view Gaussian, white Gaussian noise, because the our in is follows a 99 point uniform distribution. Uh, so these the physical parameter used for initialization and train is we have shown in the table 1. And what these are, this is the table 1, which you have the network parameter, the number of samples we have to take on, layers, sampling time, and the loss. Which parameters we have to given is the same parameters which we have given by the hardware provider, which type of robot we are using. But in spite of that, by giving the, just like we have the M1 example, we have to take the M1 300 gram, the mass of the link 1 300 gram. If the link 1 have to exhibit some outer weight or to grip some outer object, the continuously mass of the M1 is to be the change, just like. So we are not making to again and again to giving these values. So these are the result analyses in which we have to make the system response position versus time for the desired and output for the desired and actual one. So these are the particular which parameters have to checking the master stiffness, slave stiffness, master damping coefficient, slave damping coefficient, and position and their torque. So these are the parameter error estimation we have to make the delta theta curve, and these are the desired and actual. And somehow which we have to take the comparison of the tracking error between the PD controlled and LSTM, because on the comparison basis, because when we submitted this paper in RDK, one of the reviewer actually you should have to present shown the comparison with the you are presented the model, means the current one LSTM with anyone. So in the past 2 years back, for the same model we have done with a PD controller. So we have compared with this PD and proposed, and somehow the convergence rate in this LSTM model is far better. So this type of work is LSTM network delayed and noisy response and generate a control signal that minimize the difference between the desired and estimate responses. And this will be the very good results for us and to open the gate for to use how we further use to the different type of AI model in our robotics research work, just like some other strategies, just like MPDC, the predictive control mechanism, or some other with the help of different Kubernetes programs. So these are the practical implementation of the network mode in loop is also a physical teleoperated robot can offer further. So because this time we have implemented only some of simulated one. We have not particular right now hardware any on which we have to make the validate. So just the software simulated and validated work we have. But in the next results, we are trying to make the implementation of this work on the real time. So this is the work, and these are the references we have considered generally in this 1 or 2 papers in our previous work, non-linear robot calibration. So yes, sir. Yeah, Dr. Tayal, sir, any question or anything, sir, please let me know.
Hello.
Hello, yes, yes.
Can you just tell me? You have considered LSTM network, okay?
Yes, yes, yes.
So how you have arranged basically a training process?
Sir, training process in which the training process we have the particular model already established in the LSTM model. We have to take this model and to apply the approach of symmetrical time delay, not only to make the LSTM model network in which the LSTM model which I have already getting this model from the repository available. We have to make the time delay implementation in this.
Okay.
Professor, here PD represents controller.
Excuse me, sir. I
Professor.
have an urgent meeting.
Okay,
Can I
okay,
present
Professor.
my paper now?
Yes,
Okay,
Professor,
please, sir,
please.
Okay, okay, okay.
Thank you, Professor.
Okay, okay, okay. Okay, Dr. Tayal, can I leave, sir?
Yes, yes.
Okay, okay. Thank you, sir.
Yes, sir. Can I present now?
Next
Professor.
is, who is asking to present now?
Dr. Bharat Bhushan.
Yes. So paper ID 61, analysis of
Yeah.
hand.
I have to attend some urgent meeting, sir. That's why.
Yes. Please go ahead.
Okay, sir. Thank you. Is my screen visible?
Yes.
Is my screen visible, sir? Okay.
Yes, Professor, visible. Please proceed.
Okay. The title of my paper is analysis of hand shapes with convolutional neural networks for sign language recognition. These are the contents. You are able to see, sir?
Professor, it's
You
visible.
are able
Please
to see, sir?
proceed.
Please proceed.
Professor, can you hear
Yeah.
me? Please
Yeah,
proceed.
I am
Yes,
hearing.
yes,
I can hear.
yes.
Yeah. In this paper, basically, we have talked about the use of sign language, open CV, and machine learning, which helps in conveying the messages of deaf and dumb, like their hand motions, and we have to translate them into a language that is easily understandable, and that helps in conveying their messages. So this is our main motive. We have used OpenCV and machine learning. These are the introduction uh, about like gesture reputation, which is a teaching tool which helps in human to computer contact. Okay, these are some references. Then we have used convolutional neural networks, AI, and artificial neural networks. These are the basic idea is to use the signal sign recognition technique survey based on language recognition, which uses HMM based techniques. Now there are clusters and high computational demands that impede that hamper their adoption. Okay. Now interaction, how the deaf mutes and hearing people interact. This is the basic problem. Now this general movement task helps us in encouraging daily interaction among deaf mutes by accurately translating the sign language into sound or text, which can be easily conveyed. Okay. Then this is the OTSU algorithm based device which we have used to promote the Indian Sign Language for the deaf. Then we have also used intelligent sign language recognition using photo processing. Okay, this is our proposed model or work. We have used UML diagrams also, which are depicted in the next slide. Then this is the proposed architecture of our work. And this one is the methodology that we have used, that is showing the system execution right from start. Then this is the algorithm which we have designed. It consists of two stages, that is data collection, model training, and the second step is real-time open CV testing. We have used programming tools like NumPy, etc., Keras, and some Python libraries. For result analysis, we have used a table called the confusion matrix, which will be shown in the next slide. This is the confusion matrix, and this is the table of precision. Then these are some points regarding our result analysis. Okay, sir. Then these are our result analysis. First graph figure A shows accuracy versus epochs, and second B shows model accuracy and model. These are some of the conclusions. Our method successfully helps in converting hand motions into text, which can be easily conveyed, and which helps in the deaf and dumb people in conveying their messages. So these are some of the references that we have. That's all from my side, sir.
Thank you, Professor. Thank you very much.
Okay, thank you. Thank you very much, sir. Thank you. Can I leave now?
Are there any questions on this?
Hello, Bharat Bhushan Nair,
Yes, sir.
sir.
Yes, sir.
Can you tell
Yes,
me what is your specific contribution in this area? Specific contribution.
Basically, specific contribution. My specific contribution, I have assisted in algorithm design and all that. My how to that how that messages of deaf and dumb people, like hand gestures, etc., can be used using OpenCV and machine learning in conveying their messages.
Okay,
This
sir.
is
Thank you.
what
Thank you, sir.
I have helped.
Okay,
Thank you, Professor. Thank you very much.
Thank you. Thank you very much.
Shall we move on to the next paper, sir?
Yes, sir. Please. Thank you, sir.
Thank you. Next paper ID is 294. Analysis on the performance of fuzzy tuned PID control of anti-lock braking system by Priti Sharma and Jyoti Ori.
Thank you.
Good afternoon, everyone. I hope I am audible and my screen is visible.
You're audible and your screen is visible.
Yes, sir.
Yeah, thank you. So my paper. First of all, thank you to MIT and the Springer for the organizing this, and thanks to everyone for here. So my paper title is the analyzing the performance of fuzzy tune PID control for the anti-lock braking systems. So basically, what is the my table of content is the firstly we are I will be introducing the basic of anti-lock braking systems. Then there will be some mathematical models what I have used and some control designs I have done with this, and there will be some result comparisons which I have implemented. So basically, yes, I'm audible.
You're audible.
So basically, why anti-lock braking systems comes in the matters, like if we are for the cars or for any vehicles, we use the generally anti-lock braking system. So that while applying the brake, our wheel does not lock up. So why we use the anti-lock braking systems in the nowadays vehicles? So the first of all, main thing is to reduce the stopping distance for minimizing the vehicle stopping distance, and the second is the for maintaining the stability after being preventing from the locking, and the third one is the stability. So we have to maintain the peak frictional force for getting that to stability. So this is our the closed loop diagram for the anti-lock braking systems for vehicle model which I have implemented. So basically I have used the two proposed model, three mathematical model of the that anti-lock braking system. So it involves the vehicle dynamics and the wheel dynamics and the braking dynamics. So in the vehicle dynamics, we are taking the some basic Newton's law for a while, and the wheel dynamics we are taking the some moment of inertia, and we have given some basic moment of inertia to that vehicle, and we have some initial speed on which the simulation model is being tested. So as we know, the basic anti-lock braking system is a control loop feedback system. So in which I have taken the relative slip ratio as my feedback, and I will be implementing that slip ratio will be I am maintaining the slip ratio as 0.2, because at the 0.2 the frictional force will be highest in between the tire and the particular road surface. So what's the definitions we are taking as a slip ratio? It is the 1 minus wheel angular velocity and vehicle angular velocity, and also the wheel velocity we take it will be the tire torque, difference between the tire torque and the braking torque, and the and with by the rotational inertia. So basically by TBS plus one, in which I have taken these much parameters for the simulations. So in which the proportional gain I have taken the 1200 and mass of the, like I was taking the quarter car model. So mass, that's why I have taken the 50 lbs and all these parameters we have taken. The initial speed on which I have tested all these things, that was the 80.64 feet per seconds. So basically, here I was designing this the fuzzy logic based PID controller, but we initially we have to test on the PID controller. So I have implemented the PID controller also, so that we can compare the both of results. So why we need the fuzzy logic in that PID? So in the PID controller, I've taken the basic Ziegler-Nichols process for the PID tuning, in which I got the KU and TU value respectively these, and KP I got the 105, KI 75, and KD 102. And the second controller, which main I have implemented, is the fuzzy gain scheduled PID controller, in which the basically PID controller is controlled by the fuzzy rules of the fuzzy logic controller. So in which I have normalized the KD and KP values by some new KP dash and KD dash value by these values, and I have set some fuzzy rules for all these three things. So basically, controller design, what I have done with the fuzzy logic based PD controller, it is there like I am controlling the outputs of the fuzzy controller with respect to the KP, KD, and alpha value. So after as I am taking the uh, input as a relative slip ratio, so that is the basically error value. So in the feedback, I was getting the error, and like if I am taking the input of the fuzzy logic as error and derivative of error, and which I have taken the triangular membership functions from the toolbox. And for these KD dash, KP dash, and alpha, I have taken the Gaussian membership function, but the alpha I have taken the singleton membership functions. So this I got the KU and TU value respectively 75 and 4.66. So if you talk about the results, like if you are going through the only ABS control, like without any using controller, so I was getting the I'm getting the 669.6 5 feet as a stopping distance, and if I'm using the PID control, then I am getting the 379.6 feet as a stopping distance, and for the same if I'm using the fuzzy based PID controller, like fuzzy schedule PID controller, I got the 295 to 98.2 feet as a stopping distance after applying the brake. So here I'm getting the low stopping distance. If I compare the basic main thing to slip ratio, like I have to maintain the slip ratio as 0.2 such that it will get the highest frictional force. So as my main aim was the 0.2 value for the getting the stability. So for the only ABS, I was getting some perks in the in the only anti-lock braking system in the slip. But if I am using the PID, it is reduced with some extended. But after using the fuzzy based PID, it is almost getting the 0.2. As I compared the vehicle speed for both of them, like vehicle speed is getting some non-linear reducing, but in the case of the fuzzy based PID, it is getting reducing linear in a linear motion. And if you compare the wheel speed also, it is also getting the better results if we compared with the fuzzy based PID controller. If you compare the results for all the only ABS PID and fuzzy gain schedule PID controller, so first of all we are seeing that stopping distance we are getting the uh, uh, reduced in the fuzzy logic based PID control, and stopping distance also get reduced up to the 7.1 seconds in the fuzzy based controller. So my basic my basic main aim was the to keeping the value of the sleeping at 0.2, and maintaining the keep maintaining the stability of the vehicle. In the future, we can take the MPC based controller and the SMC, and also MFIS based controller we can also use in the PID control, on which I also am working now. And also we can make the hardware implementation of this, for that that will be our future scopes. These are some references I have used for these papers, and thank you.
Hello.
Yes.
Can you tell me why you have utilized PID controller, not PI?
Sir, basically, if we are using the, if we are taking the, reducing the steady state error for the rate, uh, so that's why I'm using the PID.
No, what is the specific use of derivative controller?
So basically, basically it is used for the stabilizing the system response, like the rate of the change of the error get the reduced within a
No,
particular
sir.
time of
Sir
amount.
asked why you selected that instead of PI.
So basically, I have to reduce the increase the amount of the stability at a in a particular time.
Okay. Okay. Anyway, what is the range you have utilized in the fuzzy controller in the input side?
So for the particular range,
You have taken some inputs now, so there should be
yes,
some range of input. The input will lie in the some range.
yes, sir. So that's inputs was about like, sir, it, give me something like.
Sir, am I audible? Okay.
Yes.
Sorry, yes. So that as I've used like for the minus 100 to 100 I have taken for that.
Minus
Like for the
100 to 100 to 100.
for the KP and KT, like I used for the single for the alpha value I have used 0 to 5, 1 to 5 basically.
Okay. Okay. Thank you.
Sir, one more question. Have you used the benchmark quarter car model existing in literature?
Not actually, sir. I have used just the quarter model that is
That
also available.
is available in literature. That is easily obtainable. Or
Yes,
you
sir.
developed it. Then why can't you can try only controller design alone? No, why you have computed some braking distance, etc., etc. Is it possible in that model?
No, exactly not possible. But I was just
So you have done
saying
some
this.
assumptions. Am I right?
In that particular manner, I like I have taken from the MATLAB also
No,
some.
no, sir. Designing controller to stabilize the system, it's a common problem addressed by a lot of researchers.
Yes,
Okay, along with that, you have done other parameter computation. No, that's why I'm asking. Okay, thank you, sir. Thank you very
that's I
much.
have taken as a
Yes, sir.
reference.
Thank you
Like
very
the
much.
main aim was okay. Okay.
Thank you, sir.
Yes, sir.
How do you select the triangular membership function for your fuzzy controller?
In the fuzzy logic controller, there is toolbox. We have the triangular membership function trimf. We have, like I have used the reference as a paper in which the fuzzy gain scheduling was there.
Okay, thank you very much.
Okay.
Thanks.
Are there any more questions on the same paper? Okay, seeing none, would you, is it okay if we move on to the next paper?
Yes, sir. Please proceed. Thank you, sir.
Thank you. Paper ID number 63, iBlink pattern-based drowsy driver detection system using REST-NET 50 v2 and capsule network by Rajat Tomar and Mohammad Shilvi Salim. Rajat Tomar, Mohammed Shilbi Salim. Is anybody here? Okay, seeing none, we'll move on to the paper after that, which is paper ID 161. Design analysis of dual band retina for Internet of Things applications by Asima Rajawat, Kushagra Mamta Agarwal, and Raghav Tota. Is anybody here who's presenting paper ID 61? Yes, paper ID 63. Is anybody present? Paper ID 63. Paper ID 161. Is anyone present? Okay, seeing none, I would now like to request permission to end the session, as those were the last two papers on our list.
Sure, dear, sure.
Excellent. Thank you so much, sir, for your time today, taking time out of your personal day to help us with this. It is now time to bring the session to a close. I would like to give our most heartfelt thanks to our esteemed guests for being here today. Their insight is incredibly invaluable, and we're extremely grateful that they could be here with us today. Thank you to all the faculty members in the Department of Electrical and Electronics Engineering for taking the time and effort to set up this entire conference so students like us can benefit from learning. And finally, thank you to all the volunteers for investing time in making sure this event runs smoothly in every aspect.
Thank you, dear.
Thank you, Dr. Omvir Singh, Dr. Venkatesan. Thanks a lot for giving your valuable time, sir.
Thank you so much, sir. Dr. Sir.
Thank you, sir. So we are going to wind up the session now. Thank you, sir.